Hey, I'm Christopher Payne, and today we're going to be presenting an extended, comprehensive forensic reconstruction of a WannaCry style ransomware attack. In this version, we'll go into depth about each technical component, explaining not only what we observed, but why those observations matter in real-world incident response. Our investigation approached ransomware as if this were a professional case. That means everything from the environment to the evidence acquisition process was structured around forensic soundness, repeatability, and the ability to defend our conclusions with artifacts. We treated every step as if it could be later subject to peer review or legal scrutiny. Over the next several sections, we will detail how we built an isolated malware lab, how we executed the ransomware sample in a controlled manner, how we preserved volatile and non-volatile evidence, and how each process behaved internally. Our aim is to demonstrate what a complete, end-to-end forensic investigation looks like. Project overview. The purpose of this project was to safely execute a WannaCry-style ransomware sample and document the attack using industry-grade forensic procedures. Ransomware events move extremely quickly. In some cases, encryption starts within seconds. Because of that, our design emphasized proactive instrumentation. We enabled sysmin logging, timestamp correlation, network capture, screenshot documentation, and a memory acquisition procedure before even running the malware. This version of the project overview emphasizes not only the goals but also the operational reasoning behind each step. Our environment was engineered so that we can answer fundamental forensic questions. What triggered the attack? What processes were involved? What files were modified? How did it communicate? How quickly encryption occurred? And questions like that. Everything that you would need to know about traits of malware. By anticipating these questions, we structured our system to make the answers easily discoverable. Another key aspect is repeatability. In forensics, a single experiment is rarely enough, so we structured our VM in a way that allowed us to revert to a baseline and run the ransomware multiple times, verifying consistency in behavior across runs. Lab environment architecture. Our investigation relied heavily on the architecture of the malware lab. This lab was built using Windows 11 ARM inside Parallels on Apple Silicon. While Apple Silicon introduces some nuances in memory structures, the environment provided strong isolation and reliable performance. We assigned 8 virtual CPU cores and 10 gigs of RAM so it would remain responsive under heavy loads. This is important because many forensic observations require capturing system state mid-execution, which you'll see later. Host-only networking was a foundational design choice. It allowed the ransomware to behave as if it had normal network capabilities while ensuring no outbound communication could reach the internet. This preserved both for safety and forensic visibility. Even though outbound DNS queries would fail, their presence in the packet capture would still tell us what the malware was attempting to do. That's important. We also configured the VM with manual snapshot control. Snapshots are essential not just for safety, but for ensuring forensic repeatability. Every test began at an identical system state, eliminating variability and making our conclusions more defensible. Evidence collection strategy. Our evidence collection process followed 4 formal forensic phases. The preparation phase involved enabling sysmin with a extended configuration capable of logging process creation, writing files, traversing directories, and capturing network events. We validated log flow manually before running the malware. During the execution phase, we monitored system behavior while recording precise timestamps. These timestamps served as anchors for all later correlation work. We also captured visual changes, GUI pop-ups, wallpaper changes, desktop behavior, to match them against sysmin, as well as file system artifacts. During the memory acquisition phase, we suspended the VM at the height of the encryption process. This preserved volatile evidence threads, call stacks, loaded modules that would otherwise be lost upon shutdown, which goes to the importance of suspending the VM at the height of encryption. Finally, the extraction phase involved exporting logs, event files, packet captures, before and after file samples, wallpaper images, payload executables, you get the idea. One other important thing is memory snapshots. Everything was being hashed using SHA-256 and backed up using MD5. This ensures integrity and admissibility should this have been a real forensic case.
The ransomware's GUI @wannadecryptor executable launched shortly after encryption began. Its presence indicated that the malware was not a stealth-focused variant, but one designed to notify victims immediately after encryption. The GUI included payment fields, decryption instructions, and status indicators. It also matched the behavior of previous WannaCry style samples. Additionally, the ransomware replaced the desktop wallpaper with the ransom theme message. This wallpaper modification resulted in new image files being written, these files that we later extracted and hashed. These visual indicators corroborated the the log timestamps in disk changes, giving us multi-source verification of the event sequence. Our before and after comparison confirmed full cryptographic transformation. Prior to the attack, we collected files from several categories: JPEG, DOC, PDF, MP3, and MP4. After the attack, each file had been rewritten with the .WannaCry extension and at dramatically different hash values. Full encryption is an important forensic distinction, as some lower sophistication malware simply renames files without modifying content. In contrast, our sample performed legitimate encryption, rendering recovered files unusable without keys. The hash changes, size alterations, and overwritten content confirm true data loss. These findings help quantify both impact, severity, and recovery difficulty. Even though host-only networking prevented external communication, the ransomware still attempted several DNS lookups. These attempts are significant because they reveal intended malware behavior, including potential kill switch logic or attempts to verify connectivity before propagating. Our packet capture documented each outbound request. No request succeeded, confirming that our isolation controls were functioning as expected. Importantly, the absence of SMB scanning in our environment suggests that either the sample's propagation logic required full the sample's propagation logic required full internet access, or that propagation was disabled in this variant. Documenting attempted but unsuccessful behavior is a crucial part of forensic reporting. The DNS queries we observed were primarily generic Windows service lookups and system-related domains. All responses returned no such name due to the network configuration. These queries still provide insight. They show that the malware was behaving consistently with expectations. It attempted external communication even when none was possible. This also confirmed that the ransomware recognized its inability to reach the internet, but proceeded with local encryption regardless. By analyzing the sequence and frequency of DNS queries, we gained a deeper understanding of how the malware handles network failures and what external infrastructure it expects. Memory acquisition is often the richest source of forensic insight, containing decrypted payloads, keys, running threads, and volatile structures. However, our ability to analyze the memory snapshot was limited by tooling constraints. Volatility 3 does not fully support Windows 11 ARM memory structures or parallels format memory files. Despite limited parsing success, acquiring memory was still essential. If tools evolve, this snapshot could reveal in-memory strings, process injection patterns, encryption routines, or even embedded configuration data. In many investigations, memory is the only place where certain malicious artifacts appear. Documenting the limitation is part of proper forensic transparency. Even without full parsing, the presence of the snapshot itself demonstrates correct methodology. By combining logs, CPAP data, disk artifacts, and manual observations, we built a precise timeline. This timeline is one of the strongest parts of the investigation. showing exactly how quickly and aggressively the ransomware operated. Key moments include at T0, the VM was reverted and logging initialized. At 19 hours 42 seconds 19 hours 42 minutes 23 seconds UTC, the WannaCry executable was launched. Plus 1 second later, the task executable file was created. Plus 2 seconds later, the GUI ransomware was visible, the ransom note, and the wallpaper was changed to the ransom note. Plus 2 to 3 seconds later, the encryption files appeared with the extension. The following minutes was continued encryption. This rapid sequence mirrors real incidents where defenders may only have moments to detect and mitigate an attack. Our timeline is fully evidence-backed, with every entry mapped to multiple data sources.
Alright, now time for our evidence correlation methodology. One of the most important aspects of forensic reporting is demonstrating how evidence sources support each other. Logs alone may be misleading, but logs plus disk artifacts with some PCAP data, memory, all put together form a coherent and defensible narrative so that we truly know what is happening within the ransomware. For this project, we correlated sysmon logs for process sequencing, disk artifacts for file impact verification, package captures for network behavior, memory snapshots for volatile states, limited but were preserved due to how we ran the experiment. So in the end, this correlation process eliminates ambiguity. When 4 independent sources agree on the same sequence of events, investigators can confidently reconstruct the attack. Such correlation also ensures that if one source is incomplete, for example, due to long tampering, the others compensate. Next, we have our process attribution analysis. So accurately attributing malicious behavior to specific executables is fundamental to the forensic analysis task. In our case, Explorer.exe initiated the attack, WannaCry.exe acted as the loader, TaskChe.exe performed the encryption, and @WannadDecryptor@.exe handled user interaction. This was the GUI. This level of attribution allows investigators to determine not only what happened, but why it happened. It distinguishes between automated mechanisms and user-driven errors, helping security teams target remediation and user training efforts. We documented every attribution step with logs, hashes, file paths, all to ensure that our conclusions were evidence-based. For our key quantitative findings, we want to highlight how impactful and fast ransomware attacks truly are. The malware began encryption within seconds. It affected multiple file categories and rewrote entire directory structures. It generated numerous artifacts across the system and attempted external communication even when isolated. We quantified the encryption start time, number of encrypted files, number of ransom notes, creation times, and DNS attempt types. These metrics below help organizations understand potential impact and the importance of proactive defense. So you can see that the user, after initially starting the ransomware, only had 2 to 3 seconds before the machine was completely taken over. The ransomware also specifically targeted 5 of main file types that we tested it with some external research. It seems that they specifically designed the ransomware to go after anything that they thought would be a user-made extension, which is why JPEG, MP3, MP4, PDF, and doc were our main targets. We did have no successful outbound communication in a host-only environment. This is likely due to the sample of WannaCry that we're using and the fact that that's been stripped away so that it can't spread if accidentally leaked to the main public again by someone trying to research it. And then we collected all of this from 4 evidence sources: the logs, memory, PCAP, and disk artifacts. So when it comes to our methodology insights, throughout this investigation, we learned several lessons that mirror real-world forensic practices. Mainly that preparation is everything. Without Sysmon enabled beforehand, we would have missed most process-level details. Without controlled networking, we would have jeopardized system safety. And without memory capture, our analysis would not have been possible due to us being unable to correlate events happening across the system. Today's limitations, such as ARM memory parsing, may be solvable in the future, and acquire that evidence now ensures it can be reanalyzed later if we wanted to. Finally, the value of structured documentation cannot be overstated. Our ability to construct the timeline with high fidelity was the direct result of disciplined evidence handling practices. And now it's time for our conclusions. We expanded forensic reconstruction that illustrates the full life cycle of a WannaCry ransomware attack. We built a controlled environment, executed the malware safely, captured diverse forensic artifacts, and reconstructed a detailed timeline using professional methods. While memory parsing was limited, every other evidence source remained consistent and helped our high confidence narrative. Our findings demonstrate the speed and severity of ransomware, the importance of proactive logging, and the value of multi-source correlation. This project strengthened our understanding of how malware behavior operate, forensic workflows, and investigative rigor. From all of us in the group, we want to thank you so much for listening to our presentation.